Hello, I'm Anna Mackay, and in this video we're looking at the normal distribution. Now, the previous video that we've just done was on probability density functions, and we're looking at the area under curves. Now, getting into normal statistics, this is the classic curve that we have, often called the bell curve. And what would the area underneath this curve be? It represents all the probabilities or percentages of a set of data. This curve can be seen in lots of things in nature or the gathering of data. For example, if you were to take the heights of all Year 12 students across South Australia, it would follow this pattern. So you would have the mean, the classic average, and how those heights would be distributed would mirror this distribution, which we call a normal distribution. And that can be found in lots of different things: heights, weights. If you're looking at the average time it would take a car to travel into town, and you did that, gathered that data over a long period of time, you'd find that it would approximately mirror this normal distribution. Here are some facts and properties. We're not going to go into much detail here. One I'll draw your attention to at the bottom here is essentially saying for this function, the area under the curve is 1. Notice that the bounds here are negative infinity to infinity. Also, the official formula for this function, for the normal distribution function, is a function of E, where that symbol here is mu for mean, so that's the Greek alphabet letter mu, and that's the letter sigma in the Greek alphabet. And the classic percentages to remember, approximately 34.13, we often summarise that to 34, 13.59, and so it's symmetrical about the mean. And these, if you haven't seen these before, this is one standard deviation to the right of the mean. That's 2, then 3, and then one standard deviation to the left, 2 and 3. And so most of the data, well, 99.9, I can't remember, what is that? 99.74% of the data, it says it there, lies within 3 standard deviations either side of the mean. Here's our example, lots of parts here. The chest measurements of 18-year-old male footballers is normally distributed with mean 95 centimetres and standard deviation of 8 centimetres. So we're talking about the chest measurement front to back. Here's another way of displaying distribution. The N tells us it's a normal distribution as opposed to binomial. And in terms of the two numbers written here, the first number that is written is the mean, and the second one is the standard deviation. The standard deviation is not 8 squared in terms of 64. You might see the connection back there with standard deviation and variance that we've dealt with before about how one is the square of the other or one's the square root. We're asked to find the percentage of footballers with chest measurements between 95 and 103 centimetres. I encourage you, when you do these types of questions, to draw a picture, create a visual. And what I mean by that is a quick little sketch of the distribution. So because it's normally distributed, you can just draw a rough bell curve there. You put on your mean, and then we're also going to put on the 3 standard deviations. You can draw lines in if you like. So you're going to take 95 and add on 1 standard deviation. So 95 plus 8 gives you 103. Add on another 8, 111, and the third one, 119. So that's 3 standard deviations to the right. To get to the left, you subtract off 8 each time. So the first one will be 87, then 79 and 71. Now, some of the questions that you'll do will fall exactly on those standard deviations. And on those times, you're welcome to use those percentages that you saw in that graph on the previous slide. So let's see for this first one, 95 and 103. Are they on there? Yes, they are. So if you look back at that previous picture, what was the percentage in there? 34.13%. However, let's get into the habit of writing a probability statement. Particularly in South Australia, you must write this every time you do a question leading up to the exam. That's what I'm training you up for. So between 95 and 103, we're using X to represent a randomly chosen footballer. The question that you might ask is it equal to 95 or not equal to? And same with 103. Now remember, this is continuous data being a measurement. So there is no such thing as landing exactly on 95 centimetres. If you took your level of measurement to a finer point, you could take into millimetres and even smaller. So there is no such thing as landing exactly on 95. So to be honest, it really doesn't matter if you put equal to or not. You do what you feel most comfortable with. If you think it's between 95 and 103, does that include them? Up to you. The next one I'll be a bit more specific on. So that's approximately equal to the 34% is, usually we just round it to 34, or I'll just put in brackets the 34.13%. I'm also very passionate about using the calculator as often as possible. So we're going to flick between the calculator a lot here. In the stats mode, the numbers that it's going to ask you for are the lower, the upper, the standard deviation and the mean. So let's have a think here. We've got the bounds of 95 to 103. So I'm just drawing it on here. So the lower bound is 95, upper bound is 103, our standard deviation is 8 centimetres and our mean is 95. So let's go do that in our calculators and check that it's about 34%. So we're in statistics mode, enter that. You want to select distribution and which type? It's a normal distribution, so F1 in Casio's. Your options here, it's NCD, it's the normal cumulative distribution. So we're accumulating between 95 and 103. And your data is variable unless you had something in a list, but that's not what we're doing. So your lower was 95, upper was 103, standard deviation was 8, and your mean is 95. And the answer for that is what we expected, 34.13. Next, part B is asking us to find the probability this time round. Sometimes it'll be percentages, sometimes probability. They're essentially the same thing. That the chest measurement of a randomly chosen footballer is less than 75 centimetres. This is why I find it really handy to have a quick little picture. Where is 75? 75 would be between 71 and 79, so about here. And what's the probability of a randomly chosen one being less than? So we want to the left-hand side of that. So I guess our upper bound in this case is 75. Now here's the problem. Does that lie exactly on one of these standard deviations? No, it doesn't. So this is where you have to use your calculator. Let's write a probability statement though. The probability that X, a randomly chosen footballer, is less than 75. Do we put equal to? In this case, you don't need to, but we're still going to use 75 as our upper bound. You must write out the calculator inputs off to the side. This is really important because the examiners that will be marking your exam are often teachers, and so in their day they may use a Casio calculator, they may use a TI, they may use a Sharp, Hewlett-Packard, all of the options. So you cannot put down Casio speak for your calculator, because you cannot expect your examiners to understand your calculator. So you have to put down things that are universal. This lower upper bounds are universal and can be used in any calculator. So that is what you need to write off to the side. In case you make an error, then they can go back and see what you've done and follow your error through if you perhaps put the bound in the wrong spot, or the standard deviation and mean you got mixed up or something. Our upper bound would be 75, let's put that one in, and our standard deviation and mean stay the same. Now lower bound, we essentially want out to infinity, so negative infinity I should say. So the way we write that is negative, but we can't put in a number of infinity. So essentially what we're doing is we're doing the equivalent of 1 times by 10 to the power of 98. Negative 98. So we're going as far out, which way for you, to the left as possible. On your calculator input, you do E, so it's probably a shift function, and 98. I hear you ask why 98 and not 99. Quite a few years ago, when the Casios were not as sophisticated, previous models, occasionally there was a glitch at 99 and they would crash. I don't think that happens anymore because they're much more sophisticated, but out of habit, I still do 98. Can you write in 1 times 10 to the power of 98? Absolutely you can. The other question you might ask is, these chest measurements are real life measurements, so isn't technically the smallest number we could go 0? Yes, it is. So if you prefer to write in 0, that's absolutely fine. It's just a really good habit to get into, that when your lower bound or an upper bound is not defined, so it's essentially going on for infinity, we get into the habit of writing e to the 98 or the negative e to the 98. Okay, so we're going into our normal distribution here, an NCD function. Our lower bound was negative E98. You might be asking, is it negative E98 or E negative 98? I suppose technically it is negative 98. It actually doesn't matter which way around you do that. So the E is the exponential function here. So there's that E, negative 98. I'll hit enter, and that's how it's put in. Our upper bound was 75, and the mean and standard deviation the calculator has held, and our answer is 6.21 times by, noticing, 10 to the power of negative 0.3. We'll go back and write that now. As we said, 6.21 times by 10 to the power of negative 3. You cannot write it with an E there because that means you don't understand scientific notation, or you could write, or perhaps I'll write or, 0.00621. Either is acceptable. But I'll tell you what's not acceptable is writing 6.21 E negative 3. That's not okay. This time round, we're finding the probability that the chest measurement of a randomly chosen footballer is at least 100 centimetres. Again, a quick little sketch is often handy, and this time you want 100 or more. So it's handy to see where's your lower bound, where's your upper bound when you do a little picture. A probability statement, a randomly chosen footballer, X, is at least 100 centimetres. You write in your calculator input, lower, upper, standard deviation, mean. Your lower is 100, your upper is infinity. So this time we write positive E98, standard deviation is 8, and mean is 95. I will tell you that the answer for that is 0.266, and I'll leave you to check that one on your calculators. From a group of 200 footballers, assuming the 18-year-old males, how many would we expect to have a chest measurement of at least 100 centimetres? You'll notice the connection here. We've already worked that out. The probability of a single random footballer having at least 100 centimetres is this probability. What's in a group of 200 then, how many would you expect? I guess you would expect 26% of 200. And in maths, you probably know that of is represented by a multiply. So it's 0.266 of 200, and we get 53.2, but you can't have 0.2 of a footballer, so we have 53 footballers. Part E, we're asked to find the value of K such that approximately 16% of chest measurements are below this K value. So K is going to be a number somewhere along the baseline of our normal distribution. And we want the answer to be 16% or 0.16. So the statement that we would write is the probability that X is less than or equal to some number and that the answer is 0.16. So on this picture here, where would 16% be? Well, if you start adding up these numbers, you'll find that 16% is the area here. Now, what's the bound for that? That's the standard deviation 1 to the left of the mean. So if we write that out, that K is equal to the mean number, 95, and 1 standard deviation to the left of that. So a standard deviation is 8. We're left with 87. So 87 centimetres is the number of which there'll be 16% of measurements below that. And the last one here is where we connect it to binomial statistics. Let's read it first. Out of 10 randomly chosen footballers, calculate the probability that 5 or fewer have a chest measurement of at least 100 centimetres. There's lots of information there. Often when we do questions like this, they sometimes connect to previous work. So you notice that 100 there, we've already done that. Having a chest measurement of at least 100 centimetres, what was the answer for that? 0.266. So that's the chance of one footballer, or a randomly chosen one, having a chest measurement of at least 100. We now want to know if we have 10 in a room, what's the chance of 5 or less, so we could have 4 or 3 or 2 or 1 or none, having that chest measurement. You'll get used to these types of questions with some practice. So what we actually need to define is it's a binomial distribution with 10 as our number of trials, if you like, or people, and the probability is this 0.266. I'll just write that there, n is 10, probability is 0.266. So what we're after is what's the chance that less than or equal to 5, so 5 or fewer, have this chest measurement. And again, write your calculator input. You've got lower, upper, n this time, and a probability. Your lower bound is essentially, you could write e to the negative 98, or you could write 0, because that's 0 footballers. Upper bound is 5, n this time is 10, and probability is at 0.266. Or if you've got an older version of a Casio, it accumulates up from the bottom. And in this case, that works because it's a fewer than question. So you would, I think, have the inputs of this. I'll tell you that the answer is going to be 0.973. Let's just go check this on our calculators. This time round we're using a distribution that's binomial, and it is BCD. We're cumulating up. Our lower is negative 98. Our upper was 5. Number of trials was 10, and the probability is 0.266. And aha, it says input value must be an integer. I'm guessing that's for my lower bound. There we are. So I actually had to put in 0 that time around. So 0.973 is what we said. And so we've finished this video. Join me in the next one when we talk about the standard normal distribution, which is called the Z distribution, heading into Z scores. Thank you.